Welcome everyone to our latest InterMET.digital webinar. Today's topic is about autonomous vehicles and weather data, and it's the second in a planned series of webinars by InterMET.digital exploring the business opportunities of addressing the impacts of weather and climate change. I'm your host, Dr. Sheldon Drobot, and by day I work on strategy and technology for the L3 Harris Space Systems. Today, we're going to welcome 4 expert panelists who can help you in your quest to start a weather business. Curtis Walker, a scientist at NCAR, Bryce Lambie, a data scientist and researcher working in transportation, weather, and modeling, Amanda Seams-Anderson, a scientist at NCAR as well, and Richard Foxen, formerly chief engineer at Ford UK. So each panelist will give a brief presentation, and when they've finished, we'll move on to a panel discussion and audience Q&A. We've already had some questions in advance, but we're hoping that you out there in the audience are thirsty for knowledge, and we look forward to receiving your questions via our Zoom Q&A function. We'll be looking at these questions once our experts have finished their presentations. And one final word, please bear with us if there are any technical glitches. So, without further ado, let me introduce our first expert, Dr. Curtis L. Walker. Curtis is a project scientist at the National Center for Atmospheric Research, specializing in research at the intersections of transportation, weather climate, and artificial intelligence. He completed his doctorate in Earth and Atmospheric Sciences with a meteorology and climatology specialization from the University of Nebraska back in 2018. His research interest is applied boundary layer meteorology with an emphasis on road weather applications, renewable energy, and urban meteorology. So Curtis, over to you.
Thank you so much, Sheldon, for the introduction. And hello, everyone. Good morning or good afternoon, depending on where you are watching this presentation. And so today I'm going to provide just a very brief overview of surface transportation meteorology, or kind of the study of how weather impacts the roads and transportation, but specifically with a focus to emerging technologies and challenges with autonomous vehicles. And so in terms of quantifying the impacts of adverse weather out there on the roads, at least here in the United States, this graphic shows the average annual fatalities from various weather events in the period from 2007 to 2016. And the takeaway is that when you compare the direct fatalities from weather events like flood fatalities and tornadoes and hurricanes, and compare that with the loss of life from adverse weather conditions on the roads, vehicle crashes that occur in heavy precipitation or poor visibility such as fog, you're dealing with an order of magnitude greater loss of life. Here in the United States, about 1 in 5 or 21% of all highway crashes are in some way attributable to the weather conditions, and this has significant economic, environmental, and societal implications as well. Now, in terms of specifically how weather impacts roads and drivers, there's certainly impacts directly to vehicles, such as loss of control or traction or friction, whether the road might be wet or icy. And there's also impacts to lowering the vehicle's ability to handle and maneuver in inclement weather conditions. But there's also the human aspect as well, driver behavior and human error, such as drivers losing situational awareness due to the weather conditions, or perhaps operating a vehicle unsafely for the conditions, whether this is following too closely to a vehicle in front of you, traveling too fast for the conditions, or having to take abrupt or evasive actions, whether those actions are intended or not. But in terms of solutions to this challenge, there are decision support systems out there that might assist transportation agencies with keeping the roads clear and accessible. There's also weather analytics and intelligence platforms out there that help to give not only situational awareness, but also a ground truth validation of what the weather conditions are out there. And then certainly in the emerging technology space, there are connected and automated vehicles as well. So from the other panelists later, you'll hear more about these different solutions. But I'll talk briefly about the connected and automated vehicles. And for a high-level overview, an autonomous vehicle is one that operates in isolation from the other vehicles, often using internal sensors, whether this might be LiDAR or optical sensors and cameras and radar and things of that nature. Connected vehicles, on the other hand, will communicate with nearby vehicles and fixed infrastructure for kind of that situational awareness or proxy detection, if you will. But these two technologies can be combined in what are called connected automated vehicles, and these vehicles leverage the capabilities and technologies of both platforms. Now, in terms of the levels of vehicular automation, there are five primary levels. Level zero being no automation, kind of your conventional motor vehicle out there now. But the lower levels of automation, kind of levels one and two, are where you start to introduce things like driver assistance features or partial automation, your vehicle helping you to stay in lane, or perhaps alerting you if there's another vehicle that's traveling in your blind spot next to you so you don't change lanes and strike them. But then at the higher levels of automation, levels four and five, high automation and full automation, this is where we get into situations where the driver may or may not even have the capability to still control the vehicle, and perhaps only in the most extreme situations, of which weather could be one of them. But really, at these highest levels of automation, the vehicle certainly is capable of operating in a variety of conditions. Now, in terms of how self driving cars could be better in terms of these weather impacts, certainly we have in the realm of the vehicle impacts, and these artificial intelligence algorithms can adjust things like the engine power or torque and braking to compensate for the road conditions. Or perhaps in that connected space, the vehicle can communicate with other vehicles to react and identify to changing conditions. In terms of the driver and human behavior factor, the remote sensing or sensor fusion on these automated vehicles combined with digital base maps can help identify both fixed objects and other vehicles beyond the driver's line of sight. So to always have that situational awareness of what is the position of this vehicle, and also adjust speed appropriately for the conditions. So, in terms of a broad spectrum of applications, automated vehicles have a lot of promise when it comes to, say, freight and supply chain management, in which our time and spatial scales here are going to be very broad, nationwide, or perhaps even globally. They're going to need a lot of long range planning and long range awareness of how weather conditions might change across, say, a country, or if we're talking international trade as well, perhaps across several nations. But route optimization is going to be a common thread here, regardless of the scale we're talking about. For more of an urban area, there might be, say, transit and commuting and urban mobility considerations with more regional weather, perhaps a mid range planning horizon, but again, that route optimization theme. And then emergency services, kind of this hyper local, specific to a municipality, going to be down to an individual street level. And this is going to be really short range or perhaps tactical planning as well. But again, knowing what the weather conditions are like is going to be able to optimize the route, along with things like, say, traffic conditions as well. But there still remains this danger of high impact weather. So perhaps driving on the road, you encounter a flooded road or destructive hail or even a tornado crossing a highway. And this is a challenge for automated vehicles because, well, the road is there. However, there's some large weather obstruction that you would not want to drive your vehicle through. So your vehicle is going to have some way to integrate weather information to be able to know what is beyond its own sensors, or even if it's connected to other vehicles, to know what challenges it might face. So to summarize, certainly weather does not have to dampen the implementation and development of self-driving vehicles, but it really is going to take a concerted effort of collaboration and communication between both the meteorology community and the transportation and automated vehicle communities as well. So this is certainly where there's a plethora of business opportunities on the horizon. And with that, thank you so much. And I'll go ahead and turn it back over to Sheldon.
Great. Thanks, Curtis. We'll definitely be returning to some of those great points you've raised later on. But now let me introduce our next expert, Bryce Lambie. So, Bryce is a data scientist and researcher working in transportation weather and modeling. He has over 15 years' experience in public and private weather entities. He's worked to improve road weather forecasting and verification for consumer and commercial uses. He's currently a software engineer at MyRadar, working to build consumer facing road condition nowcast and road condition climatology as inputs for predictive modeling and fleet safety. So, Bryce, the floor is yours.
Awesome. Thanks, Sheldon. Oops. Oops. Sorry about that. Here we go. Great. Thanks. So, so yeah, today I'm going to talk about verification of road condition forecasting. So this is a unique challenge. We can, it's quite easy to take a weather model and turn it into a road condition and put it out there. Verifying it, proving that it's correct. Is a little more difficult. Remote road condition forecasting, places where you don't have sensors, you don't have cameras, ensuring that you're giving quality information for those locations is a unique challenge, and that's something that at My Radar we're working to solve. First off, the ability to take a route or a point and turn it into, from your basic weather model, and turn that into a pavement temperature forecast and a road condition forecast is one of the key functionality points that most people in the industry are looking for right now, that you can actually add value to whatever model that they already have worked into their to their business for helping them reduce risk while they're out on the road, whether they're a consumer fleet, or some type of management that is responsible for safety of vehicles and drivers. We can the model coverage and model resolution is very important um, for the verification process. Different models verify differently, and in different locations verify differently. Also, the you know model inputs, we have multi-dimensional model inputs, so you have a lot of additional uncertainty, because every new piece of information that you bring in from the model to use, from the atmospheric model to use as a predictor for your road condition, adds additional uncertainty. So you really need a multi-dimensional bias correction system to compensate for that. For example, you need to be able to correct your air temperature and your road temperature, as well as other aspects or other diagnostic variables that you pull out of your model, in order to improve your road condition forecast. The first step, as I just mentioned, road temperature verification. Of course, if you're not accurately predicting when the road is going to start reach freezing temperatures, it's going to be difficult to predict the point when snow is going to start, stop melting on the pavement and start accumulating. And that's one of the key. That's the very first thing that's worth verifying. Luckily, in the United States, we have a fantastic road weather information system network, thousands of road temperature sensors across the United States, and numeric verification of your road temperature forecast using that data is key for making sure that everything downstream from that is accurate. In this example, this is one case study that we did, where our road temperature for the first 16 hours fell within under 2 degrees C for accuracy. And that's really the key, because once you start to get outside of that window, obviously your model is going to be a lot less reliable, and you're going to start missing events. Transition events from, as I mentioned earlier, when the road starts to, stops to snow stops melting on contact and starts accumulating on the pavement. That's really the key moment, right? That's when friction is going to be lost, and that's when that's when the accuracy of your road temperature model really comes into play. The Using camera imagery is one of the next dimensions that you can use for verifying your road condition forecast. The transition moment is absolutely key. On this slide, it's kind of hard to see, but if you can pay attention to where the mouse over is at the moment, you see in the top one we're still in kind of a mixed conditions. There's slushy, some slushy lanes and slushy shoulders, but in the next one we've moved over to a more frozen roadway, and this is really the transition that you're trying to model. And in this example, our forecast got it almost exactly right, and we're able to demonstrate that by using this camera data, this camera location. Another example of also finding that transition moment is right here in the upper slide, or upper image, We're still at a wet pavement forecast as snow is still melting when it hits the surface, but in the next step of the forecast, we're onto a frozen surface. And as you can see, the model is accurately predicting the moment that the road surface starts to freeze. So this is this is one of the basic methods for verifying that your road temperature and your road condition forecasts are accurate. Obviously, there's a lot that goes into this type of verification, and different different inputs can make this more complicated at different moments in time. But this it's an ongoing effort and kind of a key to any forecast that you put out there, to make sure that you have some kind of ability to prove that your forecasts are accurate. And that's all I've got.
All right, thanks very much, Bryce, for your expert insights. I'm sure the audience will have lots of questions. So we'll hold those though for now. And next, I'd like to introduce Amanda Seams Anderson. She is an associate scientist at the National Center for Atmospheric Research. Amanda has 11 years of experience with road weather research and applications, predominantly in the area of connected vehicles. But she also works in the areas of radar, wildfire prediction, and verification performance assessments of forecasts and decision support systems. She's the chair of the American Meteorological Society's Intelligent Transportation Systems and Surface Transportation Committee, and also a member of the World Meteorological Organization's High Weather Verification Task Team. Amanda, please take it away.
Great, thank you, Sheldon. I was just going to talk today about one of the solutions that we've been working on developing at NCAR called the PikeAlert system. This has been in development kind of over the last 8 or so years, and really focuses, on connected vehicles. And so Curtis brought this up a little bit in his presentation, but the basic concept of connected vehicles is vehicles that are equipped to communicate with each other and with the infrastructure to share important information for a variety of applications. One good example is the safety application, where if two vehicles are aware of the position of each other and how that position is changing through time, you can have crash avoidance applications like forward collision warnings, or alerts that maybe there's a car coming through a stop sign and not stopping. There's also the infrastructure communications, where you can get valuable information in your vehicle, such as upcoming weather conditions. And so it was around this connected vehicle concept that the PikeAlert system was developed. It was mainly developed as a data quality control system, where we're taking observations from vehicles. There's not just the positional awareness, but you can also get information like air temperature. You might see that on a dashboard of a vehicle you're driving. We can take that information in, and some more untraditional weather observations, like whether or not the wipers are moving and how fast they're moving. Are the headlights on and off? Are automated braking systems or traction controls being triggered in different weather conditions? So PikeAlert brings in all that into a vehicle data translator, processes that information along with ancillary weather conditions to provide different sorts of information like pavement condition, current or forecast. And it also incorporates an enhanced maintenance decision support system, the enhanced part being we're not just tied to road weather information system stations or other roadside stationary observations, but we can get some of that information from the vehicles as well to fill in those gaps between those existing systems. The way this works is that the vehicle data translator will receive information from connected vehicles, could be air temperatures, wipers, speeds relative to the speed limit of a road, and assigns those data to road segments. And in that way, we take a mobile platform that might be a little difficult to deal with from a meteorological point of view, and put it in a stationary location, and we can get data through time at those locations. As I mentioned, we also assign traditional or ancillary weather observations to these road segments, like your roadside stations or gridded products like the radar, satellite, or a background mesoscale gridded product. We process these together through our road weather hazard module, or the RWH, and this is where the connected vehicle data can really enhance our situational awareness of what's happening along the roadway, especially in areas where we don't have a lot of stationary observations. So an example of this is in our visibility algorithm. This is the northern part of Minnesota. Duluth is here for those familiar with the geography of Minnesota. And this is an interstate that that moves through the northern part of the state. So in the city of Duluth, our road weather hazard module is saying there's clear conditions, really nothing to worry about, but just south of the city, there's some red conditions, which are indicating fog. And so if a traveler is leaving Duluth to head south, if they just look out their window, they might not think there's any hazards to be aware of. But with the road weather hazard module, you're able to be alerted about the fog to the south. Here's an example from a camera image confirming this particular hazard assessment. And what was happening is here's Duluth in northern Minnesota in a clear area. Lake Superior here was quite warm on a cold day and some fog was affecting in. So that's why there was just such a small scale hazard along the roadway. And so in terms of autonomous sensors and autonomous vehicles, we think the connected aspect would still be useful. So rather than having the vehicles just be autonomous and operating independent of everything around them, looking more at an automated approach with connected vehicles so that the vehicles can be aware, not just other vehicles around them, but kind of that situational awareness of what's up the road. Curtis mentioned this in his presentation, you know, is there snow, is there ice? Because not only is it important for the view of the vehicle, being able to see the lane lines and stay in their lane, but also in terms of some of the automated systems like braking or how fast the vehicle can drive will depend on the friction of the pavement. Thank you.
Okay, thanks, Amanda. That's great stuff, and I'm sure once again we'll have questions very soon on that. But first, let me introduce our final expert, Professor Richard Foxen. Richard was formerly the chief engineer at Ford in the UK. He's an expert on low carbon vehicle technology and now works as a consultant assessing research projects for funding by Innovate UK. From 2015 to 2016, Richard was the president of the Institution of Mechanical Engineers, and he has been a small piece Arkwright Scholarship Trustee since 2017. So to conclude today's expert presentations, here's Richard.
All right, thanks, Sheldon, and good afternoon or good morning, everybody. And thanks to the three presenters who've gone before me, setting out a really good position on the challenges in terms of weather measurement and prediction. I'm going to talk about a slightly different thing, which is really the drivers for the development of autonomous and connected vehicles, and particularly how they fit with electric vehicles. Why are the manufacturers so keen on connected and autonomous vehicles? I'll talk about safety and emissions, how we adapt for weather factors, and then human factors. So a slightly different take on the subject from the previous three presenters. So as Sheldon said, I was the president of the Institution of Mechanical Engineers in 2015. But by coincidence, my presidential address for that year was titled From Steam Engines to Self-Driving Cars, which I really think are the state of the art of technology in terms of where we've arrived at in terms of my career as a professional engineer. So what are the drivers for why manufacturers are developing connected and autonomous vehicles? Well, firstly, it's about safety. 95% of accidents are caused by human error, and only a small percentage are caused by mechanical failure or other external factors that come into play in the accident. computers can react faster than humans and are less error prone. They don't make judgments like humans. And the growth of computing power, which has accelerated incredibly in recent years, means that cars are now really mobile computers, where around 30% by value of the car is in the computer systems that control them, compared with earlier generations. So we've got massive computing capability in the vehicles. Electric cars tend to be even more suited for autonomous control because it's much easier for the computer control system to adjust the power and torque going to the electric motor and adapt the car's propulsion to external factors than it is with an internal combustion engine. So just as we've seen in Teslas, I think electric cars will really take the lead in connected and autonomous control. Now, sensors are affected by weather factors, but probably far less than humans are. If you think about it, humans really only have vision, hearing, and touch, maybe a bit of other sensors in terms of feeling acceleration and deceleration through the way the car's moving, but they have fairly limited range of senses that they're detecting. And we need to be able to detect what's happening in lots of different weathers: fog, mist, drizzle, rain, snow, darkness, lightning. And actually, I didn't add it, but very topically this week in both North America and the UK are very strong winds. And how can an autonomous car adapt to being blown off course by very strong winds? We do have vision cameras, infrared, LiDAR to measure distance, and radar. And with all these additional sensors, we can detect far more conditions than a human can just with their vision and hearing. And if you think about aeroplane development from the earliest days of autopilots, planes could fly across the world just knowing their geographical position. But now cars can take off, fly across the world and land in foggy conditions where the pilot can see virtually nothing at the airport on takeoff, flying through cloud and then landing. So we've got a lot of sensors that go way beyond vision capabilities. And because we can also detect satellite position with satellites using GPS and navigation, the cars can know where they are to a very high degree of accuracy anywhere in the world. So sensors can detect far more conditions than human senses, and that gives us an advantage in terms of being able to move towards connected and autonomous technology. So the main benefits are really accident avoidance. As I've said, 95% of accidents are caused by human error. And through connected and autonomous technology, we can detect other vehicles, pedestrians, and any other obstacles on the road, such as trees or barriers. The car, with its vision and other sensors, can see better than humans at night because we can use infrared. The headlights can illuminate things that are visible by the vision systems on the car, which are beyond the range that the human eye can detect. We can see using radar and LiDARs through fog, rain and mist. But as Amanda said, some sensors are susceptible to weather, like maybe snowpacking on some of the sensors. And as we develop the technology, we might need to take mitigating actions like heating the sensors to stop them being packed with ice or snow. We can link a lot of the car's systems to the sensor system. So we can link the brakes, the steering, and all the other safety systems to the sensors. And that allows the car to steer, brake, and avoid things in a much faster way than a human can react to. And apart from safety, as we move towards more autonomy, we might be able to reduce emissions and improve fuel economy by having vehicles driving in platoons, That means very closely together on the highway, with far less wind resistance and drag as they're driving closely behind each other. And that's of particular importance to heavy trucks, where the fuel savings could be in the order of 5 to 10%, which is much greater than can be achieved with any other technology. So it is largely about accident avoidance, but there are 5 levels of autonomy that we need to consider. This actually repeats the slide that Curtis showed, but I think it's a really important thing to understand the 5 levels of autonomy, from fully manual driving at level 0, where the driver is in full control with no assistance at all, through level 1, where there's really simple driver assistance, maybe power steering, just things that help the driver to drive more easily, power brakes, but the driver is fully in control, all the way through to level 5, where there is full automation, the car is fully in control, and no driver intervention is possible. That's an important point. Now, at level 4, the driver can intervene and override the system if he thinks it's necessary. And I'll come back to that point towards the end, because it's an important thing to consider as we move from level 0 through to level 5. But the real reason that manufacturers are driving towards autonomy is about statistics. In the UK, and the rest of the world is fairly similar in these percentages, there are about 1,750 fatal accidents a year in the UK. And the number of fatal accidents has been falling by around 5% each year due to improvements in car and road safety. That's based on 2019 data. And we now have less fatal road accidents in the UK than we've had since cars were first invented at the turn of the last century. So we are making improvements, but we still have about 26,000 serious injuries and 125,000 slight injuries, in addition to the 1,750 fatal accidents. So if we could eliminate those 95% of accidents that are caused by human error, the numbers would reduce to about 6,250 in total, with a reduction of 119,000 accidents. Enormous numbers. So the manufacturers and the insurance companies are really keen to use the technology to make their products safer, reduce the number of deaths and injuries to the consumers that buy the vehicles and others who are impacted by them. And then if you look at, well, concerns about the technology in self-driving cars, in connected and autonomous cars, might not work 100% effectively all of the time. So I've assumed rather pessimistically that 5% of self-driving cars might cause accidents. And if we only had a 5% accident rate instead of 95% accident rate caused by self-driving cars, the number of accidents would still be reduced by 106,000. So you can see from the numbers that connected and autonomous vehicles can make enormous reductions in the number of people killed and injured, even if they can't completely eradicate them. The target that manufacturers are trying to get to is 0 accidents, and anything that we can do to get nearer to that number is only a good thing. Now let's look at the advantages and disadvantages of autonomy. The control software reacts much faster than a human because a computer works in microseconds with a very fast clock speed. It doesn't need the reaction time that a human does to react to what it's seeing before it takes an avoiding action. And the software does exactly what the programmer has instructed it to do, which is a positive and a negative. The software doesn't make any decisions other than those it's instructed to make. So there's no opportunity for human error, and there's also no opportunity for human intervention. Now, you might view that as both an advantage and a disadvantage, but in general, as I said, that most accidents are caused by humans making mistakes, it's better to take away the opportunity for them to make those mistakes. Now, introduction of the technology will be evolutionary. We should not expect to suddenly go into a dealership next year and have a 100% fail-safe, faultless, autonomous car that can never make any wrong decisions. It's going to be an evolutionary process with successive generations of vehicles having increasing levels of autonomy and increasing reliability. In general, vehicle manufacturers look at defects in terms of parts per million, where they don't want more than 1 or 2, at the very most, failures per million vehicles. And that would be an enormous improvement on the current 95% accident rate caused by humans. Ford plans to have level 5 operating with taxi fleets in Israel and in some parts of the US by 2022. It was going to be this year, but it's been delayed mainly because of COVID-19 rather than the technology. But interestingly, Ford have decided to skip level 4, where the driver can override the system, because that can cause confusion. If the driver thinks that the car is doing something wrong, he's actually more likely to intervene and cause the accident than if he leaves the system to avoid it as instructed by the software. And I guess we might debate that during the questions. But I know that Ford have decided that level 4 could be confusing, and they're going to go straight from level 3 to level 5. The technology is really here now, but it does need driver education and training in terms of how to use it properly and safely. Insurance companies are understandably cautious about the introduction because they want to know that this technology is not going to cause accidents. But as I showed you in the slide on statistics, even if 5% of the autonomous cars do cause accidents, they'll still see an enormous order of magnitude reduction in the number of accidents compared with leaving cars to drivers. The first applications are certainly going to be on highways, on motorways, which is where it's easiest to produce the autonomy. And then we'll gradually move on to other urban and rural roads as the technology improves. And as this slide says, it's going to be evolutionary. The systems will get better and better over the years, as they have in aircraft, starting off with simple autopilots through today, where we get fully autonomous capable aircraft. The systems definitely work best in good weather, places like Phoenix, Arizona, where a lot of the early testing has been done by Uber and Google and Tesla. So there's no doubt that the systems will be at their best in very good weather. But as Amanda said, even in adverse conditions where some of the sensors might be struggling, we can still get improvements from the autonomous systems, even if they're not the 100% that we're trying to achieve. So autonomous and connected vehicles are seen as strategically important to the automotive industry to meet what they call mega goals of 0 fatalities on the roads. They actually have 3 mega goals, which are 0 fatalities, 0 emissions, and complete choice for consumers to choose cars that suit their needs. But the 0 fatalities should lead to reduced insurance costs. And there's an interesting question that longer term, we might get to a point where we can reduce vehicle weight and therefore improve fuel economy and emissions, because we could get rid of all of the heavy safety systems, the crash structures and the airbags that are needed to protect people in accidents if the cars can assure that they never actually get involved in an accident through the reliability of the autonomous systems. That's an interesting point to debate as well. And if we eventually get to the point where the cars are so capable they can never have an accident, we may not need to insure them, which is an interesting challenge for the insurance companies. So the introduction is going to be gradual and not a big bang. And every year we'll see continuous improvements in the capability and reliability of the technology. I have a level 3 car that can steer down the freeway without me intervening. It actually tells me to put my hands back onto the steering wheel because it's not ready yet for full autonomy. But each year that I get a new car, I see the improvements in the control that the vision and LiDAR systems achieve in terms of keeping the car in the lane, steering it, braking automatically, and keeping a safe distance from the car in front. So I've talked quite a bit about the similarities with autopilots on aircraft. And really, we should view the way that cars are going as very much the way that aircraft have developed. And there's a joke within the aeroplane industry that in future, aeroplanes will only have one pilot and a dog in the cockpit. And the pilot is there in case something goes wrong with the automatic system. And the dog is there to bite the pilot if he touches any of the controls, because it's far more likely that the pilot will make an error than the automatic systems. And there's been a lot of evidence in recent years from air accidents that many of them are caused by pilots overriding the automatic systems, misinterpreting the data that they're receiving and crashing the plane as a result. And if they'd left the automatic system switched on, the plane would have carried on flying safely. So thank you for that. And I'll be happy to answer questions. I'll hand back to Sheldon. Thank you.
All right, thanks, Richard. That was great. And again, it's time for our Q&A. So for everybody, if you look at the bottom of your Zoom window, you will see the Q&A window there. Please just type in your questions. They are coming to me and I will parse them out to our expert panelists. So let's get rolling with some of the questions. First to Bryce. And Bryce, is camera imagery only used for verification, or can it also help improve condition forecasting?
So yeah, that's a great question. The camera imagery feedback after it's been classified can actually be used to improve models and find additional variables and data within the atmospheric model through like EOFs or even just basic correlation work. You can use the camera imagery to find other things that you might not be focusing on in the model at the moment that might not be as obvious. So yeah, in that sense, it can provide a feedback loop that helps improve the models.
Okay, thanks, Bryce. All right, Amanda, the next question is for you. Is PikeAlert running operationally, and if so, where?
So yes, PikeAlert is running operationally. From a more research and stakeholder engagement standpoint, we're operating in a number of states in the US, including Alaska, Nevada, Wyoming, Colorado, Iowa, and we have some other states that should be coming online here fairly shortly. In terms of actual operations, as part of the Wyoming Department of Transportation's connected vehicle pilot deployment, PikeAlert is running on Interstate 80 for them, and it's ingested into their traffic management center to help them keep up to date the weather conditions along I-80.
Okay, great. Thanks, thanks, Amanda. All right, Richard, back to you for the next one here. And the question is, how will traffic cope with a mix of autonomous and non-autonomous vehicles on the same road?
Well, I think that's a really good question. And it's an important one that while autonomous vehicles are very much in the minority and small numbers, they have to be capable of operating with existing non-autonomous vehicles. And that means all of the systems, the software and the sensors have to cope with conventional traffic where they're not really connected together in the way that Curtis and Amanda talked about, and they are independent, but they have to operate wholly with the existing fleet, and they will better do that. One of the concerns about the early adoption is that because of that, the software tends to be rather conservative, and the drive cycle is very cautious. So you always end up with the autonomous vehicle giving away to more aggressive drivers who are trying to dominate them on the road. I think, as I said in the last but one slide, the progress will be evolutionary. And as we learn from that, the software will improve year on year.
All right, fantastic. Okay, so Curtis, next question from Jonathan Smith in the audience. What are the existing relationships between the weather and autonomous vehicle communities?
Certainly, thanks for the question. So, at least presently here in the United States, there are some business to business type of partnerships that are increasingly developing. Some of the autonomous vehicle companies and manufacturers out there are actually starting to hire or at least advertise positions for meteorologists and atmospheric scientists to join their ranks. But I think one of the challenges going forward is that right now, a lot of these relationships are kind of fragmented and not really coordinated. It's kind of, at least from the outside perspective looking in, maybe coming as an afterthought. And so I think we really want to see more of a kind of coordinated and unified front across sectors in both communities, from academic, public, and private as well, to really kind of advance these technologies in all weather conditions.
All right, thanks, Curtis. Bryce, next question to you is from Dave Hammond. It's a bit long here, so I'll read it, and then there's kind of two questions really. So, Bryce, what is your approach for validating road surface temperature forecasts on a route-based or microscale forecast, where you're modeling surface temperatures in between ARWIS stations? And do you see cost-effective low-power infill RST sensors that utilize new IoT communications as a means of providing this additional in-situ data? And could such additional data points be easily ingested into your model validation process?
Awesome. Yeah, thanks, David. That's a good question. So first, the verification of locations, where we don't have RWIS data. Obviously that's complicated. What we can do is do holdouts, right? We can forecast for locations where we do have RWIS data, but then not use that RWIS data in our modeling, and then come back later and use that for validation. And once that model is validated, we can apply that to locations where we don't have RWIS locations or RWIS data, and then feel confident that that it holds up. That's kind of the classic way of doing this kind of verification. And your point about bringing in real-time sensors, absolutely, and that's a major goal that we're working on always, to bring in more ground truth data. It's difficult. We've had a couple of case studies over the years where we've had some road temperature sensors on vehicles and collected data. Quality analysis is quality control of that data is a big part, and then just quite frankly, volume is the major problem, because you'll have a vehicle drive down a section of roadway, and then that's it. You have that one observation for when they go down that roadway, and you don't get any more until later. So I think we're just not quite there yet, where there's enough of this mobile road temperature data out there, and I'm hoping that in the future, as it becomes more widespread, we'll be able to do more of that. But currently we're pretty limited.
Okay, thanks, Bryce. All right, Richard, back to you. We have another question from Jonathan Smith that is a little provocative, so let's see what you think. So Jonathan asks, haven't AVs been hyped up a bit? So recently we've seen Uber have plans for AV taxis, and Waymo, which initially made a big splash, has confined its activities to the Phoenix suburbs. So are these cases where the companies maybe got out a little in front of their skis, or what do you think? And I know you've talked a little bit about Ford, so what's your perspective on that?
Yeah, I think that's an interesting question. The way I look at this is we get really exercised over the 10 accidents that have happened in the world using autonomous cars. But no one talks about the hundreds of thousands of fatalities that happen around the world every year. We just take it for granted that people get killed on the roads. But we get really, really agitated when we think that a few of them, maybe 5 to 10, have been caused by a self-driving car. So I think we are getting sidetracked by the issues that the autonomous companies have had. The chief executive of Waymo is actually a friend of mine who used to work with me at Ford Motor Company when I was there in the late 90s. And I think, if anything, the delays to things like Waymo and Uber have more to do with the business equation around the ability to make money out of autonomous systems and sell them to the large OEM manufacturers than they have about the capability of the technology to work. So it's a very complicated world in terms of selling technology to very large companies who tend to be naturally risk averse and want to know that everything's going to be 100% safe. And getting to that level of confidence is a challenge. And it applies inside the companies as well as outside, thinking about the statistics that I talked about earlier. We get exercised, as I said, about a really small number of failures in autonomous vehicles, but we don't even talk about the very large number of people that are hurt every day on the roads.
Yep. Interesting points. All right, Amanda, back to PikeAlert. Is this available to the community? And if so, how would they get the source code?
Yes, so a number of pieces of PikeAlert are open source and are available from the United States Department of Transportation's open source application development portal, OSADP. If you do an internet search for that, you should be able to find it. However, the forecasting expertise and some components that have been developed at the state level would be available through partnership with NCAR. We really prefer to work in a research capacity with stakeholders and help deploy PikeAlert and make improvements to it. So contacting me is always a way to get the PikeAlert code as well.
All right, and we'll have that information available on your contact from Ian. Will talk about that at the end of the webinar here, so we can get back to that. So thank you. Okay, Curtis, a little bit of a different question here. How does climate change play into automated vehicle development?
Thank you so much for the question. Richard kind of alluded to this in his presentation that, one of the hallmarks of autonomous vehicles is the capability to reduce emissions. Many automated vehicles out there now are either hybrid models or are totally electric. And so there's certainly that benefit as well. But, another unique way that climate change could play into the automated vehicle equation is you're going to develop these algorithms and capabilities under a particular set of conditions. However, these same algorithms need to be flexible so that if those conditions change, for example, in some of our talks earlier, we've talked about snow and ice and how that could impact sensors or vehicle maneuverability. But certainly, in a changing climate, say perhaps warmer areas that see less snowfall, those algorithms may no longer be as important. Similarly, though, perhaps with changing weather patterns, you'll have areas that receive more precipitation or less precipitation than they currently do. And so when AVs were implemented there and it was safe to assume a set of conditions, if those conditions change, the AV is going to need to be able to adapt and accommodate them. So definitely climate change, AVs can help climate change, but I think it'll also be an important challenge worth noting as well.
Right. Yeah. Thanks, Curtis. Great answer. All right, Bryce, we're going to come back to you for the next one. This is from Mark Flolid, the co-founder, executive vice president, and chairman at Global Weather Corporation, a place I know you know well. So Mark asks, I would like to know more about use cases, modeling approach, variables forecasted, how vehicle data is being used, and how you verify forecast quality. That's a big question. So just try and hit the main points, I think.
Yeah, yeah, absolutely. No, thanks, Mark. Yeah, so the main the main drivers right now are, I think the first part of the question is, what variables are forecasted. In our current product, we focus on road temperature, road condition. We also do things like delay risk and crosswind. blow over risk, things like that that are kind of what we consider secondary, not directly modeled, but more inferred from existing atmospheric data. So the ones that road temperature and road condition and how those are modeled, this is statistical modeling processes. We have several different layers of machine learning models that are trained for different things, and kind of stack on top of each other to produce different levels of output until we get to our the kind of the main component of the road condition. And so really what we're trying to do is kind of track energy in the system. That's the key, is when is road temperature going to cross over to a freezing mark? That's impacted by the amount of energy that's been put into the roadway system, and that's the kind of information that we're trying to tease out of the model. And we have that from things like cloud cover and rated forcing and things like that that the model is predicting. We're just trying to track that in kind of a more closed system that is the roadway. I mean, of course, it's not a physical model. We're not trying to model the physics of it. We're just trying to say, these are the inputs that we know will contribute to the output that we're trying to get. And that's kind of the first step. The next step is, as I said earlier with the camera imagery, this gives you your ground truth, and you can take that moment and you can take cross sections out of the model, using like EOFs or even just correlations. You can find different components of the model that are contributing information to to your final answer, and that's really how we kind of figure out which components we're going to pluck out of the atmospheric modeling system. And then for verification, yeah, I mean, it's each one of those, some of those can be verified independently, and some of them can only be verified based on what your final output is, with the camera imagery. And so that's kind of an ongoing challenge to find more sensor data for verification, which is why more mobile data would be ideal. But currently we really only rely on RWIS data for verification rather than mobile data.
All right. Yeah. Thanks, Bryce. Great question, Mark. Richard, back to you. Kind of a related question, one you can play off a little bit. So what happens in the event of adverse weather affecting the sensors and causing the system to malfunction?
The systems will always try to fail safe. Well, they will always fail safe. And so they may alert the driver and say the driver needs to take over. The other benefit of the number of sensors we have is there'll be a lot of redundancy in the system. So maybe one or two of the systems may be struggling, but it'll still have other ways, such as satellite GPS, radar, and vision systems that may be less affected by the weather than the sensor that's struggling. So the redundancy will still allow the system to operate. And it's only when it doesn't have enough data to continue operating safely that it will then alert the driver that he needs to take over.
Okay, yeah, fantastic. All right, let's see. Our next question is for Amanda. This comes from Graziano Coppa. Hopefully I said the name right. How important is uncertainty in sensors measurements, especially environmental sensors like temperature and humidity in this field? And secondly, to what is being done to improve sensors accuracy and traceability to international system of measurements?
A very good question. I think a lot of it depends on the application of the data. So from kind of a PikeAlert current conditions point of view, we can tolerate quite a bit of uncertainty. For example, if the air temperature is a few degrees off of the true value, it doesn't tend to affect things too critically. However, if you're looking to do something like assimilate vehicle observations into a numerical weather model, then the tolerance for inaccuracy or uncertainty is a lot lower. And you also have to account for the uncertainty in your data assimilation process, which means you need to quantify it. So a lot of moving parts there. And unfortunately, because you're getting data from vehicles, it's not well maintained. You know, there's dirt on the sensors, there's ice and snow, and it's really a secondary to anything that the car is doing. So we really don't have the luxury that we do at maybe an RWIS station of having maintenance and really adhering to gold standards and standard units of measurement. So we kind of just have to take what we get and deal with it.
Okay, perfect. Thanks. Curtis, back to you. This one comes from Hedi Agrebi. How do you explain, or how do you know that autonomous vehicles are actually more safe than regular vehicles in good weather conditions?
Thanks for that question. You know, I think it comes back to, and Richard has said this certainly, I think it really comes back to that human error aspect as well, that there's a whole range of conditions that drivers presently have to adapt to. And we've certainly seen that they, unfortunately, don't always accommodate that. I do think, though, it is an open question. And that's really, I think, what all of us are advocating for, is that we really want to see certainly more and more involvement across communities in terms of really verifying that yes, the autonomous car can be safer. But I think that as Richard showed in kind of his statistics there, that even if we say that an autonomous vehicle is as safe as a human driver in inclement weather, then there's still kind of the non-weather safety things as well, such as people not paying attention, distracted driving, impaired driving, and things like that as well. But specifically in weather, it's a good question, and certainly I think the community is hoping to answer it in the coming years.
Okay, yeah, thanks. Richard, back to you. This one comes from Sue Haupt. So to what extent are the OEMs, or the car companies, striving to work with meteorologists to deal with these weather issues?
Not an area of my expertise, I'm afraid. I'd like to sort of preface this answer by the fact I left Ford 15 years ago, and I am speaking today in a personal capacity, not as an employee of Ford Motor Company. So I do know what's going on. I would assume they are working with meteorologists, but I don't know the detail of what they're doing to make the sensors robust. It's all about making things robust to failure and minimizing failure rates into the parts per million rather than the parts per 100 or parts per 1,000, which is what we see with human error on the roads today.
Okay, great. Anybody else on the panel want to comment on that one?
I'll certainly just share my experience. I kind of come at it from the other way as a meteorologist who is hoping to work with the OEMs. And as I mentioned earlier to the question about what have the relationships been, I think it is certainly networking is definitely helpful. And the OEMs definitely seem interested in it. I think there's a lot of perhaps regulatory and policy concerns in the coming years that are perhaps precluding a more serious weather consideration.
Okay, yeah, great, thanks. All right, Bryce, this one's to you from Bo Zvatek. What kind of connectivity solutions are envisioned for A, vehicle to vehicle, and B, vehicle to supplemental databases such as weather data services? And then C, is it concerning when connectivity is lost?
Yeah, I mean that's a great question. I think for there's been a lot of work in this with radio technology that has kind of been out there for years. But in my opinion, I think most of this will probably just go to 5G. Will be the only standard just for cost and things like that. When connectivity is lost, I don't think that automated vehicles are going to be, stuck with just need a connected access to, weather data every second. So I think that, there's going to be enough computing power on the vehicles that if they lose connectivity and don't have the latest and greatest weather information in that moment, that they'll still be able to make, good decisions themselves. So I don't think that losing connectivity is going to be the biggest issue. I think it's going to be more an issue of how are those algorithms that are going to be running on board going to, are they going to be reliable in all conditions, not just when connectivity is lost. And so I think that's the real challenge, rather than making sure a vehicle is always connected, just making sure that the decision-making process, when it comes to weather, that is reliable.
All right, thanks, Bryce. All right, Amanda, this one's for you. What's your view on the quality or resolution of currently available weather information and its compatibility with the need for autonomous vehicles?
So my personal view on weather information is there's never, ever, ever enough, but that's not realistic. So I think every year we're getting better quality data and especially better resolution of data and dealing with maybe a little bit of degraded quality. For example, I know in the UK Met Office has been working on using citizen scientists in their own backyard weather stations to kind of do a better job of covering the country. And again, that's not going to be the gold standard and we have to deal with that, but it's great to just have that data out there. In terms of the automated vehicles, I think a lot of what Bryce was saying is relevant here, where it would be great if your vehicle got some information on whether there was a tornado ahead or it was about to drive into, a complete whiteout blizzard and won't be able to see the lanes at all. But in the absence of that, there's going to have to be algorithms that do something besides just stopping in the middle of the road. So I think rather than getting more weather data, they're going to have to learn how to deal with it if they just don't have any, because it's a big world and we just can't cover all of it, unfortunately.
Yeah, absolutely true, especially in certain parts of the world, right? So, okay, Curtis, this one is from Alana Dackler. Now, don't you think the statistics on accidents may be a little bit skewed toward human error because, there's simply too few AVs on the road to provide a large enough sample size?
Certainly, it's a very good point. I might punt over to Richard and see if he has a comment too. But I'll say that, absolutely in statistics and analysis, certainly we can do our best to try to normalize relative to the number of human drivers on the road, the number of AVs, to try to make more meaningful comparisons. I definitely think in the coming years, as AVs are out there on the road and do get implemented in more and more different diverse conditions, certainly we're going to get, if there might be a question about the sample size now, I definitely think we're going to get there in the coming years to where we can absolutely draw conclusions and say compare it on a one-to-one basis. But Richard, maybe if you have another thought there.
No, I agree, Curtis. I mean, as I said several times, the development's going to be evolutionary. And at the moment, the number of vehicles operating out there to gain experience is really minuscule compared with the hundreds of millions of cars on the roads worldwide. So it's going to take a while. We will learn year by year. And as we learn more and more, the systems will get better and better. I don't think it's a reasonable expectation to think that we can go from a fully manual aeroplane to one that flies around the world fully autonomously, and I did mean aeroplane, not car, in a single year. People have maybe rather misplaced expectations of getting from a fully manual car to a level 5 fully autonomous car in such a short time frame. We are going really fast compared with the 100 years that cars have been around, but we shouldn't expect to solve every single problem in 1 year.
All right, thanks. Richard, this next question is also for you. And technology is great, but it's not free. So especially as we look at world economies today with COVID and maybe things are expensive and people are struggling with jobs, what's the deal with technology and autonomous vehicles? Is this stuff going to be expensive? If I want to buy a car in 5 years, how much more am I going to be paying for it?
Yeah, it's moderately expensive, but it's not really expensive. In rough terms, it's probably no more expensive than the technology that we have to fit to every car to meet emissions legislation, which people don't realize doubles the cost of the engine. So So if you think about it, it's a fairly powerful computer with a number of sensors. So orders of magnitude, it's roughly the cost of buying a high-end PC with some sensors to go with it and putting it in the car. So maybe $1,000 to $1,500. It's not $10,000 to $15,000.
Okay, yeah, fantastic. All right, so Amanda, we've got another question. It's maybe a difficult one. We'll see if you can answer it and then go to the rest of the panel. It comes from Rajendra Singh, and Rajendra is asking, what are the telecommunications challenges we're facing to make this a reality? I thought it might be interesting for you, given your experience in Wyoming, which is perhaps a little more rural than many other states.
Yes, fortunately I have internet today, so that's fantastic. In terms of automated vehicles, I think earlier Bryce addressed this really well with the fact that they're just going to have to be able to deal with the loss of communications. There can't be a reliance on connected vehicles getting weather data from outside sources or any other data. At some point, they'll have to be able to operate autonomously. From a connected vehicle standpoint, the traditional solution has been dedicated short-range communications, or DSRC, at least in the United States, and that was at the 5.9 gigahertz band. It was saved for road safety applications. That's going away. The FCC ruled that some of that could get parsed away to 5G. So I think, again, to what Bryce was saying, it's going to have to go 5G, it's going to have to go cellular and web. But also in some of these areas where you don't have that, the best you can do is some of these radio backhaul networks that some of the more rural states in the Western US have to deal with loss of communication. So it's always going to be an issue, I think.
Yeah, and I anticipate that being in other parts of the world a challenge as well. So we'll have to see how that goes. So thank you. All right, Richard, this one comes from Ben Pickering, and it's specific to Ford. He's wondering, do you believe that Ford really will achieve its goal of having a robotaxi fleet in the year 2022?
Yeah, I've unmuted. Yeah, I've seen that recently. As I said, I no longer work for Ford, so I don't have the inside scoop. But I believe they are going to get to 2022. They originally had targeted 2021. That was delayed because of COVID-19. They will have a fleet. How big it is, I don't know, but I'm pretty sure they will have a fleet operating on normal roads somewhere in the world.
Okay, great. All right, Bryce, this next one comes from Verve Carsisto, and this is probably more of an opinion piece for you, but they're wondering what will be the way to define when the weather is so bad that the driver should take control. Do you think that's going to be some predefined threshold value, like rain intensity over a certain value, or something else?
Yeah, that's a great question. I believe it'll probably be based on sensor type input. At a point when the lidar system cannot see, past a certain distance due to, either heavier precipitation or something else, or also, friction sensors when the wheels start to detect slippage or any other type of traction loss. I believe that those are going to be the types of hard events that the vehicles will, just say, the driver has to take over. I think there are going to be, softer events where the vehicle will be making decisions that, the driver might not agree with and might just decide to take it over too, say, oh, I feel comfortable driving faster than the automated vehicle does. So I think, yeah, I think it'll be a very soft line, and I think there'll still be drivers who want to make their own decisions in certain instances, and then, but of course, I think there will also be sensor input at times when it just the vehicle will force the decision.
Great,
Can
great.
I add to that, Sheldon?
Yeah, sure thing, Richard.
That may be the case in the near term while we're still developing the technology. But as I alluded to with my last slide about the pilot and the dog, I think we'll get to the point where the autonomous vehicle is by far the safest option in the really adverse weather conditions when it's verging on unsafe to drive. If the driver takes over in those conditions, he will be less safe than the autonomous system. And the real answer, if it is so extreme that the autonomous system can't drive, is the car should stop and fail safe at the side of the freeway, because the driver is more likely to cause the accident than the autonomous system. And if it's beyond the capability of the autonomous system, then the vehicle needs to pull over. Planes don't have that option, but they can fly to a safer part of the sky if there's extreme turbulence, for example.
Right. Okay. Great. Okay, Amanda, kind of a similar question here. This one comes from Daniel Johns. And given there is an effect on vehicle sensor performance by weather, do you think that to improve safety in poor weather, road authorities will need to legislate speeds of AVs in those conditions, or do you think the AVs will self-legislate in some way?
That's a really good question. Kind of from my experience in my little corner of the world, legislating speed is not always the easiest topic. On some of the freeways here, we have variable speed limits where in adverse weather, the road authorities can drop the speed limit from 75 miles an hour down to 55, 45, whatever is appropriate for the weather. And there's a lot of pushback from drivers on that and whether that's enforceable or not. And in the same way, I would hope AVs would self-legislate their speed for a couple of reasons. One, I just think that in some areas there will be a lot of pushback on that. And secondly, speed harmonization is so important for avoiding crashes and fatalities. And so especially in a world where there's a mix of AVs and manual driving vehicles, the AV needs to be at a speed that is in harmonization with the other vehicles, or it could pose a hazard on the roadway. So I think it would need to be self-legislating with the vehicles around it and just making the car work in adverse weather before you put it out on the road.
Yeah, perfect.
Yeah, I completely agree with that, Amanda. When you get to about 30% of AVs in the fleet, that regulates the speed of all of the other drivers. And as you said, drivers tend to not adhere to the lower speed limits in adverse rain. If the vehicle is connected to the network and is instructed to drive slower, and you've got enough of them on the road, that'll make everybody drive slower. And it's the speeding cars in the adverse weather that cause the accidents.
Yeah, that's going to be a really interesting thing to roll out in the coming years. So
it is.
We shall see.
Like external speed control, when seatbelts were first introduced 50 years ago, people used to worry about getting trapped in their cars in fires and resist wearing them. Now, if you ask your kids if they'd go in a car without a seatbelt, they'd say, "Are you crazy, Dad? How could you possibly consider going in a car without a seatbelt or an airbag?" So it's a progressive acceptance by society. And in 50 years' time, people will be asking the question, "You mean you used to be able to drive at any speed you liked in the rain? How crazy is that?"
Yeah. Good point, Richard. So let's stick with you. We got a question from Mike Gadd here that I think is pretty interesting, and it's a two-parter. Bryce, I'm going to give you the second part of this one, but the first part, Mike says, as an aviation safety specialist now working with drones, is zero accidents a realistic goal, given that systems will fail no matter how high the integrity or cost model used?
I think the goal's entirely right. Just like we want zero emissions, and we say, "Oh, well, but all of our cars emit gases and power stations emit gases," but the goal of getting to zero for entirely renewable energy is got to be right. The goal for zero fatalities has got to be right. If we were to start selling automobiles from scratch and we didn't have 100 years of history where people were killed on the roads, do you think we'd be allowed to sell a vehicle that can cause a fatality today? I don't think we would. And people don't accept risk like they used to. So I think zero fatalities has got to be the right objective. At the moment, we're in fatalities per 1,000. I want to get to fatalities per million or per billion. And if we got to a point where we were talking about there have been 3 fatalities in the 7 billion people in the world each year, that would be a pretty good place to get to.
Yeah, get to the point where we know the names, right? They're said and
So
people
you got
know
to
them. That'll
start with
be
the
something.
target.
Yep. Okay, great. Thanks, Richard. All right, Bryce, there's a part two to this question that I think is perfect for you, and it relates to security of the backhaul network. So how do you see the backhaul support systems and services being secured against bad actors mainly, right? And how do they make sure they're robust so that they're not going to fail at a critical moment?
Yeah, that's a great question, and I think that that's a problem that industry really needs to solve by bringing in other experts. I think that's one of those kinds of cases where they need to really rely on cybersecurity experts and other types of there's people out there making great headway and securing corporate assets and those kinds of things. And I think that kind of knowledge, needs to come into this industry at some point. And hopefully manufacturers are planning that far ahead at this moment. But if not, then I think that's we need to open it up to more experts for that case. Yeah.
Okay,
This
great. Thank you.
cybersecurity is a really important area that I know all the manufacturers have been working on for at least the last 15 years. Quite a long time ago, Chrysler had some well-publicized problems where people were hacking into their systems and overriding the power steering systems. And since then, there's been a load of emphasis on cybersecurity and making hack-proof systems. And one way they do it is they employ hackers, and the people that do these bad things and know what their procedures are to get in through the firewalls to make them more robust. But there is a load of effort going on in that area.
Yep, absolutely. All right. We've got our last question to Curtis here. And Curtis, how would you encourage anyone looking to break out into this unique industry? Where do they get started?
That is a great question. I'll say if you have an answer, let me know. But joking aside, certainly I think networking is important. Attending webinars and sessions such as the one we're on now are definitely great ways to, network and meet folks and kind of, ask the experts and get some different unique perspectives. And I'll say in my personal experience, trade shows, conferences, obviously COVID has taken away the in-person nature of those meetings and venues, but there's still certainly the online capability of Zoom and webinars and still ways to network. So I really think network away, kind of attend sessions like this, reach out to folks, get their contact info, and have the conversation about whatever your business interest might be, and see if you can maybe develop a partnership or start a business together.
Okay, thanks, Curtis, and thanks everybody, all our panelists, and everybody in the audience. And this concludes today's webinar. And again, we'd like to thank you for joining us. And we really hope you gained some useful insights into the interplay between autonomous vehicles and weather data. Now, if you want to re-listen or have a friend listen to this, a recording of the webinar will be available in the next few days, and we will notify all of those who registered for today's event. So looking ahead, the third webinar in this series will take place on Wednesday, the 24th of February at the same time as this one. And we can reveal that our topic will be on applications of artificial intelligence in the weather sector. And full details will be available shortly on the website. So finally, if you have any further questions that you'd like to ask the panelists or want to get in touch with them in any way, please email them to us at ian@mediageneration.co.uk. And I think Ian's putting his address up on the screen, and then he can get the questions to the panelists. And one final thing, for future webinars, if you have any ideas on topics you're interested in that are related to the theme of business opportunities and addressing the impacts of weather and climate change, please let us know. So with that, I will say good morning, good afternoon, and good evening for wherever you are. Thank you again so much, and we will sign off now.